Welcome everyone to today's webinar, Pinpointing Numerical Issues, a tool for the diagnosis and explanation of ill conditionings in LPs and MILPs. So today you will be hearing from Dr. Ed Klotz, Senior Mathematical Optimization Specialist at gurobi-modelanalyzer, and I will hand it over to you now, Ed.
Okay, thank you, Angela. Let's start with our agenda here. So I'm going to start by giving introduction and motivation as to why we're interested in having the tool Angela mentioned. Then we'll talk about some underlying fundamental concepts that we really need to understand to make use of the tool. We'll look at three common sources of ill conditioning, and then we'll focus on the tool itself, starting with a quick start guide. It's very easy to get started and use this. And then deal with the fundamental challenge, which is that it sometimes provides very large explanations of ill conditioning, and we would want to develop some skills in interpreting those explanations. And then I'll wrap up with a discussion of where we think we might go with this and try to summarize. So in terms of an introduction, well, if you're building models, you sometimes encounter unexpected or counterintuitive results from the solver. And, this can wreak havoc with your plans in terms of your schedules for getting out the application in a timely manner. So an organized approach to deal with the unexpected is very helpful. And we constantly want to expand our tools and knowledge to help explain such results. Gurobi already has an infeasibility finder that is good at explaining unexpected infeasibilities in the model. But what other explainers might help our customers? Well, based on our customer tickets, a tool to explain ill conditioning could be helpful as well. So that's the background. Let's now focus on some fundamentals that we can use to create such a tool. Let's first talk about the condition number of a square matrix. So we want some measure of the conditioning of a square linear system. Here, bx equals little b. And, this type of system of equation shows up quite a bit in the simplex method, which Gurobi relies upon so heavily. And so the way we're going to do this is we want to measure for a given change in the input, in this case to the right-hand side, delta b, what is the resulting change, delta x, to the computed solution of this linear system of equations? So we take this perturbed system here and we expand it out, and then we can cancel out the terms from the original system. And from what's left, we get that the perturbation to the solution is the inverse of our basis matrix times the perturbation to the input. We now can apply the Cauchy-Schwarz inequality to both this last system and the original system, and we get these two inequalities here. We then take the product of the two left-hand sides, and that will be less than or equal to the product of the two right-hand sides, since all the quantities here are non-negative. And then we rearrange a bit, and we get this relationship between the relative change in the input and the relative change in the computed solution. All right, so it makes sense to define the condition number of our matrix as the product of its matrix norm and the matrix norm of its inverse, as we see here. So what this condition number gives us is a magnification factor of this relative input error that gives us an upper bound on the error in the computed solution. which we see over here on the left. And note that this is an inequality, so it's a worst case limit. It's not an exact amount. And let's now think about what the implications are of this definition, given the computing environment in which gurobi typically resides. So in that case, well, with 64-bit doubles, which is almost certainly what your computer is using, the smallest representable number in double precision is 10 to the minus 16th. So just representing your data can introduce rounding errors of that level. And if you have a condition number of 10 to the 10th or greater, this inequality up here says that we have the potential for error in the computed solution to be on the order of 10 to the minus 6th, which is what gurobi's default feasibility and optimality tolerances are set to. So this is a key threshold because basically we don't want solver decisions based on round-off error. And if the condition number is above 10 to the 10th, that's the lowest value where that can happen because of this error in representing the data. Now, typically, because this is an inequality, gurobi usually has no trouble with condition numbers in the 10 to the 10th to 12th range, but there is potential, and once it gets above that, ill conditioning is more problematic. So another way of viewing this condition number definition is that the change in input can be viewed as the flap of the butterfly's wings, and the condition number here gives us some sense as to whether that's going to create a tornado elsewhere or not. All right, so now that we have this definition, how can we use this to come up with a computational procedure to explain ill conditioning? So we have our definition here, and we make use of the following theorem, which relies on the notion of the distance to singularity for a matrix. So we say that the distance is the minimum relative perturbation to that non-singular matrix that makes it singular. So it's a relative distance to singularity. And there's a theorem that says that that distance has a reciprocal relationship to the condition number. And we can now use that. So in that regard, let's consider this linear system down here, which is saying, give me a non-zero linear combination of the rows of my matrix B that is 0. If B is singular, such a vector Y will exist. But if B is non-singular, this system is infeasible. But if B is non-singular and close to singular, we can find a solution for the problem of minimizing the infeasibilities of this system, where the sum of the infeasibilities is small. And that gives us a measure of the distance to singularity of this particular matrix B. And in particular, we solve that subproblem, which is an LP, and we get a solution Y that minimizes the sum of infeasibility. And any element of Y that has a value of 0 identifies rows that can be filtered out from an explanation of infeasibility. So another way of saying this is that the support of Y provides a row-based certificate of ill conditioning. We can do likewise for a column-based explanation. The procedure is essentially the same, except that our problem here, our system here, now involves taking a non-zero linear combination of the columns. So this is the only difference. Everything else is the same. In this case, the support of Y provides a column-based certificate of ill conditioning. And then lastly, ill conditioning can also occur in a simpler case where you have pairs of almost parallel rows or columns in the basis matrix, and that will explain the ill conditioning. And then you don't need to solve an LP to figure that out. You can just look at angles of pairs of matrix rows and pairs of matrix columns. And if their angle is close to 0, they are almost parallel. And that can be expressed as this condition here involving the difference between the inner product of two rows or columns and their norms, and having it be non-zero but small. And the gurobi-modelanalyzer package that we're going to discuss provides functions to easily find either row, column, or angle-based explanations for ill-conditioned basis matrices. Okay, so let me take a quick pause right there for any questions where questions that aren't related directly to the slides will be deferred till after the hour.
All right, we have a question from Henry, which is, doesn't finding the Y for the problematic rows or columns have the same problem of ill conditioning if the A matrix is ill conditioned? So how do we accurately find this Y?
Yes, so I didn't go into that detail, and that's a valid question. But basically what I do is when solving that problem, I set very specific parameters designed to deal with numerically challenging problems. And so far, that has not been an issue. The point is that that subproblem won't necessarily have all of the basic columns in the ill-conditioned matrix be basic in its optimal solution.
And we have one more question that just came in, which is about huge coefficients in the restrictions relating to row or column angles being a source of ill conditioning.
Let's defer that. We'll see plenty of examples of that in subsequent slides. But yes, that is an issue, and we'll see it.
We can move on.
Okay. All right. So the next thing is, it turns out there are 3 common sources of ill conditioning that show up over and over again, and it's very useful to look for them. And what is the first one? Exactly what we were asked about, namely large matrix coefficient ratios. And this is particularly true when those rows and columns have common intersection. So here we have a little 2x2 example. M is some sort of big M value, and we see that it appears both in column 1 and in row 2. Here is its inverse. And drawing on our definition of condition number, we see that the condition number is going to be M squared or potentially higher if this is sort of embedded in some other bigger part of the matrix. So what do we want to do about this if we encounter this? So first is avoid unnecessarily large big M values. We have a tendency to use big M's to model like logical conditions or fixed charges, and we sometimes choose much bigger values than are actually necessitated if we took a closer look at the variable bounds in our model. And in that case, you want to reduce the big M as long as you don't compromise the meaning of the model by making it, reducing it too much. And then the second thing is to avoid unnecessarily small units of measurement. This results in unnecessarily large values. So, a lot of times if you have a large budget model, you don't want to measure things in dollars. You want to measure things in, say, hundreds of thousands of dollars. That would be one such example that enables you to reduce the unnecessarily large values. Okay, source number 2 is inconsistent or unnecessarily truncated problem data calculations. Now, this involves values that are supposed to be the same but have slight differences. And these can arise because models can evolve over time, or different parts of the model may calculate things differently. And those different calculation methodologies, well, they might be equivalent under perfect precision, but they might no longer hold under finite precision. So all of these things can lead to slight differences And then also truncation that is unnecessary. So here's a good example that's very simple. It's almost certain that these two underlined highlighted numbers are supposed to be the same. But we have two issues here. First, they're calculated inconsistently. So they disagree out in the, what is that, 9th decimal place. And secondly, they were only calculated to 9 base 10 digits. 64-bit doubles support 16 digits. So we could have provided more precise information. So what does this mean? Well, it means that we introduced a bigger perturbation than is necessary to our input. And we saw how perturbations relate to the change in the computed solution given the condition numbers. So by providing the data more precisely, we basically introduce a smaller perturbation, which is less likely to be problematic. And as we'll see in a subsequent slide, we actually could have eliminated all the loss of precision in this case and done an even more precise representation than 16 digits. All right, so what are the remedies here? So calculate your data in double or higher precision to limit the round-off errors and hence the perturbations. In that regard, take care to try to avoid adding and subtracting numbers of dramatically different magnitude, because basically under the hood, that is doing some sort of shifting to equalize the exponents that loses a bit more low-order precision than if you had very similar exponents. Now, that shifting doesn't occur with multiplication and division, but you still want to take care to avoid dividing small numbers into bigger ones. Gurobi does that itself in its basis factorization quite extensively. Now, the next remedy is to use integral data whenever possible. So in the previous slide, we talked about how you want to provide 16 digits of precision in your data rather than less. But at least in this example, we can see here that these two numbers are meant to be 1/3 and 2/3. So we can just multiply through by the least common multiple of the denominators, which is 3 in this case. And now we get this all integer representation of this constraint, which is more precise with no round off error at all. So that's the best approach. And then lastly, one sort of related issue as far as precision, when you're writing out models to, say, investigate things involving ill conditioning, is remember that Gurobi's MPS files have higher precision than our LP files, which have some limit in the number of decimals that it will write out. So when trying to reproduce behavior, use the MPS files. The LP files are really more for model inspection than solving numerically challenging models. Okay, so let's now come back to this notion we talked about just a moment ago about using integral data whenever possible. So in our little example here, it was pretty easy to figure out that these decimal numbers were 1/3 and 2/3. Okay, fair enough, but I don't know about you, but I don't know what the fractional representation of either of these two numbers is. Now I can go look on various resources and get some information about how to convert repeating decimals and actually even non-repeating decimals like this. But the main thing is that there is a Python package for doing precisely that task for us. And it's very easy to use. So here's a simple function that is available in the ill conditioning explainer package. So you can just call it there, but I'm showing the code here in case you want to, use it yourself for other tasks. And the way this works is you just specify a Python list of the values you want converted, and you pass that list into this function, and it gives you the nearest approximate fraction of the numbers of interest. And now you have the denominators you need to convert these values to integers in any constraints or other data values in your problem. All right, so that looks like a big step forward. Well, what about these numbers? Okay, well, let's run the program and see what happens. Well, what we get is a bunch of huge ratios here. And if we start multiplying through by least common multiples of denominators to get integer coefficients, we've basically moved the problem back to the previous source of trouble involving large matrix row or column ratios. So that's really not the answer in this case. So what are these numbers? Well, these numbers are actually 16 decimal representations of various well-known irrational numbers that we see here. So first of all, all floating point numbers are rational in 64 bits or any other finite bit precision. So we are going to give up some accuracy, but again, we do want to go with 16 decimal places. So make sure to use all 16 base digits. I can't tell you how many models I have seen that have this number here, this 0.707, and they stop, say, around here, and they're leaving money on the table in terms of their precision. And then the second remedy is to check for rescaling to all rational coefficients. Now, unlike the previous cases, there's no guarantee that this is going to happen, but it's worth checking. And I illustrate with a very simple example where we have this constraint here on the left with irrational coefficients, but by multiplying through by square root of 2, we turn it into one with all integral coefficients without any loss of precision. Now, I called these three numbers that I've described here irrational numbers, but they actually are special irrational numbers in the sense that they all involve trigonometric data. So you want to think about, other trigonometric data and other irrational values. You want to keep the same thing in mind. All right, and then the third source of high condition numbers is what we call a cascade or long sequence of transfer constraints, like is illustrated with this example basis matrix. So clearly the norm of this basis matrix is very modest. So if this is ill-conditioned, it's going to be because of a large inverse of the basis value. Well, at first glance, you wouldn't think that there would be large values in the inverse of the basis, but it turns out the last column of the inverse of the basis has coefficients as large as 2 to the n minus 1, where this is an n by n square matrix. So this actually is an ill-conditioned matrix, and we'll dig into why momentarily, but I also want to mention that there are other cases that also have these cascades where it's going to be less clear than what we're about to see now. Okay, so let's just compute the inverse of the basis of one of these matrices. I'll illustrate with a 4x4 example, but I think the pattern should emerge already as to why this inverse is ill-conditioned. So we go through the standard inverse calculation. We append an identity matrix, and we start pivoting. So we pivot on element 2, 2 here, and we then have to eliminate the element above the diagonal by multiplying through by 2. That multiplication hits this coefficient in row 2, column 3, and we get this coefficient of 4 or minus 4. We now pivot on element 3, 3. We have to eliminate that -4, but in doing so, we're going to multiply this -2 by 4, and we get a -8. So, and then we do our final pivot, and our inverse has this 8 value here. So what we're seeing is that in the upper right corner of the work matrix, as we do these eliminations, its value increases by a factor of 2 with each new pivot. So inductively, we can see that for an n by n matrix, at the end of this process, the upper right hand value of the inverse is going to be 2 to the n minus 1, and thus B inverse for n of just modest size is going to have a big matrix norm. Another way to see this is to just write out the constraints, the transfer constraints individually. And we note that in consecutive constraints, they share one of the two variables in common. So we can start basically substituting variables in these equations into the preceding equation. And when we finish that exercise, what we see that this says is that the first variable is basically 2 to the n minus 1 times the last variable. In other words, we have a hidden large coefficient in the model and a hidden large coefficient ratio. All right, so what are the remedies for these hidden mixtures of large and small coefficients? In our previous two cases of sources of high condition numbers, we had some very set remedies. Unfortunately, I have not figured out any sort of obvious thing that you can just say, well, do this. It's more about looking at your model and assessing why the activities at the start of this sequence are basically being rescaled to much larger values at the end of this process. And so the analogy I like to say is you've got something in your model where, say, you have a 16-ton chunk of metal, and you have a bunch of intermediate processes that somehow yield an end result of just billions and billions of paper clips. And you need to figure out, well, what's going on there? So I don't have a concrete answer. It really depends on the model. Okay, so any questions about this section before we go on to actually using the package and how to make use of it?
Yes, there is one question, but maybe it's not directly related, but I think that's a good one to answer. There is a question about the scale flag parameter that gurobi has. The question is that, does the scale flag parameter fix the sources of ill conditioning? And if it does, to what extent?
So that's a good question. And the answer is it can fix the ill conditioning in some cases. I'm not going to go into the details of exactly why. In particular, scale flag 2 is a good choice, but it doesn't always. And the best analogy we like to use is that using the scale flag parameter treats the symptom. And especially if you're in a rush, that may be the best way to do it. You need to get the model out the door. But the explainer tool and some of the recommendations we just went through, those are treating the actual causes, and those tend to be a more robust way to address the problem. So that's how I would respond to that question.
Yep, there is no other question. I think that you can continue.
Okay. All right. So let's now move on to the package, first with a quick start guide. So you just have a standard pip install command to install it. You need to also have a gurobi license. And then there's a very basic usage. There are API functions that, while they support other arguments for more advanced usage, the most common approach is you just import gurobi-pi, import the model analyzer tool, read in your model, solve it. And then you can get a row-based explanation by calling this kappa explain function with just the model itself, or you can call that function with an additional argument to ask for a column-based explanation, or you have this angle explain routine, which is a separate function that will, look for almost parallel rows or columns and return basically sets of tuples of those rows or columns. So that's it. So when you run this, what do you get back? So for the row and column-based explanations, you get LP and MPS files of the explanation itself. So in terms of understanding what this is, let's start with a real well-conditioned problem that's real small, that's publicly available, where what I did is I added a constraint to create the near parallel scenario that we've described before. Now, let's talk about what this output looks like, what this output means relative to your original model. So what we're doing here is we're listing the rows of the basis, but we're doing it in a particular order. So, we found the minimum infeasibility to this problem here on the right. And what we're listing here is we're looking at the Y values, the values of the certificate of ill conditioning, and we're sorting the constraints by magnitude of those Y values. The idea being the ones at the top are going to be more important in the explanation. And that's actually what happens here. And then our convention here is that we take the original constraint name and we prefix it by the actual Y value that was derived when we minimize the infeasibilities in this system here over on the right. So that's what this is. And in this case, what we see is that really only the first two constraints need to be looked at, because the contribution of the remaining 5 constraints, since all the coefficients are actually on the order of 1 and the multipliers are around 10 to the minus 10th, basically have little contribution at all. So it basically gives us the two rows that are almost parallel, and that is the explanation of ill conditioning. So we see here that the only difference between these rows is that they're opposites of each other, but one of them has a 1 coefficient for XO2, whereas the other one differs from 1 or from -1 for XO2 slightly. And then for a column-based explanation, you instead get an MPS file. In this case, the column-based explanation is harder to interpret, but we do see that the problematic coefficient is involved. And the convention is the same. We list, the columns of the basis corresponding to the non-zero elements of this Y vector, this certificate of ill conditioning, and we do it in order. And we prefix the column names by the actual values in that certificate. And then lastly, for the angle explainer, you just get back a set of tuples of the almost parallel rows. And not surprisingly, for this simple example, it picks them out. So in this case, there were no almost parallel columns, so you got an empty list. And then we also return the actual model associated with the basis matrix. All right, so what are the takeaways from this simple example? So first, try row, column, and angle-based explanations, because some will be easier to interpret than the others. Sometimes one method provides a much smaller explanation than the other. I think for most of us, row or angle-based explanations tend to be easier to interpret. All right, so let's now talk about the situation where the explanation is not so simple like we saw in that basic use case. So you can get larger explanations, and at first glance, they may seem hopeless and, you know, really difficult to interpret. So we want to develop some tactics to effectively interpret them. And I'm just going to illustrate with 3 models. So all of these are publicly available. And the first is going to be this LP relaxation of a MILP model. And just looking at the problem statistics, we already sort of have a hint as to what is likely to be involved, because we see one of the 3 usual suspects here, namely large coefficient ratios. And then interestingly enough, though, Gurobi's pre-solve model doesn't have this problem. This isn't actually surprising, because Gurobi's pre-solve is very good at reducing big M coefficients that are unnecessarily large, but it doesn't always succeed. And so that's why it's useful to think about that yourself. Anyways, when you run this on the original model, the optimal basis condition number is 10 to the 22nd, which is really big, but it's very manageable. Oh, excuse me there. On the order of 10 to the 7th for the pre-solve model. The row-based explanation has over 600 rows, but that's still better than the column-based explanation, which has almost 4,000 rows. The angle explain routine doesn't find anything. So let's look at the row-based explanation. It's still better. And what we find is that most of the constraints look like these 3 here, and just have plus or minus 1 coefficients that don't really promote any growth in the activity levels. These seem unlikely to be the direct cause of the ill conditioning. They may interact with other constraints, but by themselves, they're not going to cause problems. So there's only a few remaining constraints in the explanation if we exclude these from consideration. Those are the ones that turn out to have these big M values. And we see in particular that this big M value for C7034 not only intersects this constraint, but C7034 does appear in this other constraint. So it's exactly that first case in terms of sources of ill conditioning. All right, so the point is that we could just stop here and say, all right, we see what the problem is. We need to reduce these big M values, but let's try to understand the complete explanation to sort of develop our skills in that regard. One thing that's interesting is that the multiplier values for this first group of constraints are actually a factor of 10 larger than the multiplier values for the constraints with the big M's. And anyways, let's take a closer look. And one tool that can help in this regard is the package includes a matrix bitmap function, which will display a bitmap of the non-zero structure. And in that case, what we see is most of the matrix has this bidiagonal structure, and then right at the end, in the bottom right of the bitmap, there's a few more complicated constraints. So what that's telling us, and if we look at the explanation, we can confirm that algebraically, is you have a whole bunch of these row doubleton constraints. And if you look at them, what you see is that consecutive constraints always have one of the 2 variables in common. So we see this over and over again for the hundreds of constraints that look like that. So what we could do is we could just add up all these constraints. They all have the same multiplier value, So we could basically compress them down into this one combined constraint down here at the bottom of the slide. And it would be equivalent in terms of explaining the infeasibility. So basically, we can just look at this as our explanation. And if we now just take the linear combination given by these multipliers, we see that what's left is indeed a very small vector. So indeed, that explains the ill conditioning. And again, the takeaway is just that we need to address those large big M values on the order of 10 to the 10th. All right, so what's the summary or takeaway from this? So it was the unnecessarily large big M values in the original formulation that was the cause of the problem. It wasn't really problematic here because Gurobi's pre-solve recognized that it could reduce those big M's to more reasonable values that did not compromise the meaning of the model. But Gurobi can't always do that. So understanding how to do that yourself can be helpful. We have a presentation, if you attend one of our Gurobi days, that goes into great detail on how to figure that stuff out. So those are the takeaways for the model. Regarding the ill conditioning explainer itself, the key points are you don't always need to understand every constraint in the explanation. Look for one of the three sources, one or more of the three sources of ill conditioning, namely large ratios, imprecisely truncated or rounded data, or these so-called cascades in subsets of the explanation. There's a matrix bitmap function that can help you understand the full explanation, and constraints with only plus or minus one coefficients while involved in the explanation probably aren't the actual source of the ill conditioning. Let's move on to a second one. This is actually a sub-problem that Gurobi created from an open problem, but it is available in the package. The problem statistics indicate everything is benign. Turns out there's no obvious sign of imprecise data. You get all sorts of inconsistent results in terms of declarations of feasibility or infeasibility, depending on how you vary pre-solve and LP algorithm settings. The optimal basis condition number is 10 to the 33rd. In this case, again, the row explanation is much smaller than the column-based explanation, and the angle explain routine doesn't bias anything. So let's look at the row-based explanation. Well, this turns out just to be a very slightly more complicated cascade than the one we looked at earlier. So as we had in the original example, you have this situation of consecutive constraints share a single variable. So just like we had it in our original example, we see it here. Really, the only difference is in the original example, some of the variables had coefficients of 1, whereas that's not the case here. But if we just divide through, we now see that we're basically in exactly the same scenario, except we have a coefficient of 3.73 something instead of 2.0 like we had here. So this one is just an ever so slightly more complicated example of a cascade. And then let's move on to the last example. This is also publicly available. The problem statistics, both for the original and the pre-solved model, don't show any indication of a large coefficient range or other problems. Turns out the optimal basis condition number is on the order of 10 to the 38th, but is only on the order of 10 to the 6th for the pre-solved model. Again, in this case, the row-based explanation is much smaller and is our best bet. But even though it is modest in size, as we'll see, at least I had some trouble getting a handle on it. As an aside, the other thing I want to mention is, while I've only seen a handful of models, so the evidence is anecdotal, when you see condition numbers of 10 to the 30th or higher, usually that means cascades rather than large ratios or imprecise rounding. All right, so if we look at our bitmap, it seems sort of consistent with a more elaborate cascade. So cascades have had this sort of diagonal structure, but it's not simple bidiagonal anymore. It's sort of a more complicated diagonal structure. So this is somewhat consistent with the notion of a more elaborate cascade of constraints. So that's what I was looking for. But when I looked at the explanation, even though it only had, 57 constraints, I had trouble getting a handle on how the cascade was coming about. Now, this is an electricity model. So this is about satisfying demand by basically turning on generators, and generators tend to have this notion of ramp up where it takes time for them to come up to full power. So it looks to me like what's going on here, and looking at a paper confirmed this, that basically the first index of these variables was for a particular power source, and the other second indices were time periods. So there seems to be some connection between these so-called link constraints and these ramp-up constraints, but I had trouble sort of getting it organized just by looking at the explanation. Well, what else can we look at? Well, the problem stats tell us that the norm of the basis matrix is going to be modest. So if it's ill-conditioned, it's got to be happening from the inverse of the basis. Well, the inverse of the basis is relevant in the calculation of both the primal and dual variables. So we can look for large primal and dual values and see if those will help us identify how to order the variables or constraints in the explanation. It turned out there weren't any large primal values, but we do find some large dual values with the same power source and time period. So here are some of those dual values. Here, the underlined ones are the ones that were in the explanation. And so I made use of those basically to figure out what's going on. So basically, as the time period decreases, the dual values were increasing. So I reordered the explanation with these link and ramp up constraints ordered by time period. And now here's the constraints, and we see how the multipliers are getting progressively smaller as the time period increases. So I'm going to start with the last time period and work my way back. And basically, I'm going to start pivoting on these rows of the basis. So I start with the last time period, and we look at the next constraint over, and what we see is there's one variable in common in the two constraints. So let's eliminate that variable. We multiply the first constraint here by the suitable value, in this case, minus 165, to eliminate this. We now get a combined constraint, and then we can now again identify two variables in common with, or a variable in common with the combined constraint and the next constraint in the ordering as we work backwards to the second to last time period. And again, we pivot, in this case, multiplying by minus 330 to do the elimination. And we can continue this process each time looking for the variable in common with the combined constraint and the next constraint in this ordering we've constructed. And we just keep doing that. And after about 5 of these, well, I think a pattern has emerged here. And it's all about, well, we have these coefficients that are growing, but is that, some form of linear growth, which means they won't grow too big, or is it more of an exponential growth? Well, to get a handle on that, our first pivot used a coefficient of 165, and all these numbers here that are growing are multiples of 165. And if we look at the multiple, here are the multiples listed over here on the right. And well, these are part of the Fibonacci sequence. And there's a formula for the nth Fibonacci sequence. And what we see is we do have exponential terms here, with this one being really the dominant term. So we do have exponential growth. So that's why we get a huge condition number, because basically, given the number of these constraints, we are going to get condition numbers with exponents of over 10 to the 30th. So everything's consistent here in terms of this interpretation, in terms of the dual values we got and the condition number we got. So this one, though, was a bit of a sort of algebraic exercise, and we need to reconnect ourselves with the model itself. There's still some questions that aren't answered by that exercise, such as, well, why did the optimal basis for the pre-solved model have a much smaller condition number on the order of 10 to the 6th? Well, with some additional investigation, we discovered that by looking at the pre-solved model, which gurobi allows us to get, pre-solved removed all of these variables that were basic in that cascade that was so problematic. Next question. The original models had huge dual values at optimality, but no such huge primal values. Well, why was that? And you can write out solution and basis files at optimality, and what you discover is that the variables that were basic that created the growth, they were basic, but at lower bound of 0. So as long as they stay at 0, the huge condition number was relatively harmless. It didn't adversely affect solution quality. And this model is not known as numerically challenging. Gurobi and all the other solvers that I've seen have no trouble with this model. But the key point is that if the model had somehow been changed so that those variables could take on positive values, you could very quickly get some huge primal values. But what I think is going on is those just don't make sense in the physical system. It would be like a really long ramp-up phase that would be brutally expensive, and you would never do practically. So the ill conditioning is there, but we never really hit it. So I think that we have a better understanding, but in some sense, you don't need to really fix the ill conditioning in this model, although it would be useful to understand from a modeling perspective what this means. And then as far as lessons for the interpretation of the explanation, this illustrates how these cascades can be harder to interpret than large ratios or imprecise rounding. And then again, condition numbers above 10 to the 30th usually do indicate a cascade. Looking at patterns of multipliers and large primal or dual values can help us. And again, thinking about the underlying pivoting operations associated with computing the basis inverse can help us as well. So first, as far as roadmap goes, we are already looking into other ways to automatically reduce the explanation size. including automating that combining of constraints that I illustrated in the first example, and other ways to filter out constraints with small multiplier values. That includes things like considering eigenvalue and singular value-based methods. And so we'll probably have a new version out within a couple months that will have some of these features in it. And then we'll see how people respond to this. Right now, it's really a model development and troubleshooting tool. But if people respond really well and we get the sense that it would be useful in an application, we'll move it beyond Python, put it in our C API, and hence make it accessible through all our APIs so that people can use it in an application as well. So summarizing, the package gives you 3 different methods to compute an explanation of ill-conditioned basis matrices. Different methods provide better explanations for different models. We saw how there were 3 common sources of ill conditioning. So if you remember those can really help you when the explanation is significant in size, because you don't always need to understand the full explanation. You look for signs of the 3 common sources. And then the other trick we saw was you combine constraints that don't need to be looked at individually to reduce the size of the explanation. And you actually look at the multiplier values in the certificate of ill conditioning. All right. Well, thanks for listening. Give the package a try. Let us know how it works.
Great. Thank you, everybody, for joining us. And again, thank you to Dr. Ed Klotz. We hope to see you in our next webinar. Bye, everybody.